Hello there, and welcome to Sleepy Cosmic Podcast, where we wander beneath velvet skies, following ancient light on its unhurried path through time. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe. No pressure at all. If you'd like, tell me where you're listening from and what time it is where you are. Now, dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. Out beyond the orbit of Jupiter, where the sun is no brighter than a distant lantern, a traveller from another star drifts inward. Astronomers call it 3I Atlas, the third confirmed interstellar visitor ever seen. The first two passed quickly, tiny fragments of ancient systems. But this one, this silent giant, is different. It moves with a deliberate slowness, as if tracing an old memory through our solar plane. We've been watching it for months, a faint green speck gliding across the star fields, tugged by the sun's gravity. Soon, on October 29th, it will slip behind the solar fire, hidden from every telescope on Earth. That day marks its perihelion, the closest point in its orbit, and perhaps, just perhaps, the moment when it decides whether to stay. In physics, gravity is a conversation between mass and distance. The sun's pull is stronger near its heart, where the heat and radiation rise in waves. Most visitors simply bow once and move on, following hyperbolic paths back into the dark. But if Atlas were to slow down, even a little, the sun could catch it, pulling it into a permanent dance, an orbit that would make it part of our solar family. We don't know what it will do. We don't even know what it is, not really. But there's poetry in that uncertainty, a fragment from another system, carrying secrets of unknown worlds, arriving in our neighborhood like a message written in the language of light and motion. Imagine it there, far from us yet drawn nearer every day, its surface frozen, crusted with carbon dioxide and water ice, dusted by the long drift through interstellar night. Each molecule on its surface may have been born under a different sun billions of years ago, and then carried here across the quiet gulfs between stars. Astronomers call these objects interstellar interlopers, remnants of planet formation flung away by the gravity of their home stars. Most wander forever, unclaimed by any system, but every so often one crosses paths with ours. The first, Oumuamua, came in 2017, a cigar-shaped shard that moved like nothing we'd ever seen. The second, Borisov, was a proper comet, leaving a tail as it passed. Atlas is the third, a visitor whose story is still being written. Out there, sunlight touches it faintly, enough to warm the surface and release gentle streams of vapor. These wisps carry information, spectral fingerprints that tell scientists about its composition. Each observation adds a note to the score, the reflectivity, the path, the subtle wobbles. Yet each answer opens another question. To think that an object from another star system could find its way here, crossing light years of emptiness, is to feel the scale of cosmic chance. Space is vast beyond our comprehension. The distances between stars make even the fastest objects crawl like drifting snowflakes through eternity. For something to arrive at just the right angle, at just the right time to fall under our sun's gaze, it feels like coincidence stretched into miracle. The Atlas mission name came from the Asteroid Terrestrial Impact Last Alert System, a survey scanning the skies for anything that moves. When it found this traveller, astronomers saw immediately that its path was not bound to the sun. It came from the void beyond the heliopause, where the solar wind fades and the interstellar medium begins. From that first detection, Atlas has carried a quiet mystery. Why here, now? Why this trajectory that threads so close to our planetary orbits? Each night, as we look up and track its faint trail, we stand at the edge of understanding, a reminder that our solar system is not isolated. It breathes. It exchanges material with the galaxy like lungs exchanging air. Perhaps Atlas is simply one more exhale of the Milky Way, a bit of dust and frozen carbon returning home. Or perhaps it is something more deliberate, a messenger from far beyond the reach of human time. We don't need to decide tonight. We can just breathe with it, feel its steady pull inward, and imagine what waits behind the sun's bright veil. If we could stand on its surface, we'd see the sun as a brilliant disk, 5 times smaller than from Earth, yet still dazzling against the black. The stars would not twinkle. There is no air to scatter their light. Every grain of dust that rises from the surface would float outward slowly, following the path of gravity and light pressure. Over millions of years, that dust will join the faint, thin haze that fills interplanetary space, the zodiacal glow you sometimes see after sunset, a ghostly band stretching along the ecliptic. In this way, Atlas becomes part of us. Its material may someday settle into our own orbit, fall into the upper atmosphere, and burn in a brief whisper of fire. Cosmic matter recycled again, memory folding into memory. The universe rarely rushes. It favours long arcs, quiet accelerations, and patient returns. And so we wait for October 29th, for the moment when this wandering ice might decide, through physics alone or through something we cannot yet name, to stay. As we wait, we can imagine what it feels like out there. Silence so complete it feels like pressure. A darkness, not hostile, just endless. And through it, a single object gliding toward light, carrying the chemistry of another sun, the fingerprints of another time. When it vanishes behind the solar blaze, we'll lose sight of it for weeks. But losing sight is not the same as losing wonder. Somewhere behind that glare, Atlas will make its choice, and when it returns to view, we will look again, measuring its path, its brightness, its whisper of motion. We will ask what changed. Tonight, we rest beneath that same sky, knowing that something ancient is on its way home, or perhaps becoming part of ours. In the wide ledger of celestial statistics, Atlas should not exist. Not here, not now. The cosmos is full of wanderers, but most are small, fleeting specks. The odds of encountering a behemoth like this one, 20 kilometers across, are almost laughably low. Astronomers run the numbers and shake their heads. A visitor of such size should appear perhaps once every 10,000 years, and yet, within barely a decade of modern sky surveys, here it is, rolling silently toward the inner system as if drawn by a hidden invitation. For context, our telescopes have been scanning for interstellar objects seriously for only about 10 years. The technology became precise enough to trace faint movements against the stellar backdrop, tiny dots shifting from night to night, revealing trajectories unbound to the sun. That we found something so large so soon suggests either astonishing luck, or a hint that our models of what's out there need revision. In science, probability is a map of ignorance. When we assign numbers to rare events, we're often describing how little we truly know. The early universe forged untold billions of rocky fragments when planets first began to form around newborn stars. Most of that debris stayed local, locked by gravity into stable families of worlds and moons. Some was hurled outward by gravitational slingshots, ejected into the dark between systems. Those expulsions, stretched over billions of years, populate interstellar space with frozen bodies adrift in perpetual night. Still, for one of these exiles to intersect our tiny volume of sky is unlikely. Imagine a single grain of sand thrown into the air above the Sahara and landing precisely on another grain miles away. The odds are small, yet the cosmos is patient. Over deep time, even miracles find a rhythm. When astronomers first estimated Atlas's size, they based it on brightness. A body that shines so strongly must either be vast or unusually reflective. The initial figure, 20 kilometers wide, meant that its nucleus could outweigh the asteroid that ended the age of dinosaurs. If that measurement held true, Atlas would be one of the largest active comets ever seen, and by far the largest interstellar visitor known. But brightness can be deceiving. A small object covered in reflective frost can mimic the glow of a larger one. So researchers refined their measurements, accounting for reflectivity, or albedo, and the spread of dust around the core. Even then, the numbers stayed impressive. Atlas remains a giant by any standard. The enormity of it invites questions about survival. How does something this large drift for millions of years through interstellar space without colliding, fragmenting, or dissolving into dust? In the galactic wilderness, each close pass by a star system could alter its path or strip away its surface. For Atlas to arrive intact means it travelled the void relatively undisturbed, protected by the sheer emptiness between suns. Interstellar space is not entirely empty, though. It carries wisps of gas, dust grains, cosmic rays, and the faint breath of magnetic fields stretched across light years. Over time, these tiny interactions sandblast a traveller's surface, darkening it, sealing volatile ices beneath layers of carbonized dust. That protective crust might be why Atlas still holds so much frozen material to sublimate now. When we calculate probabilities for events like this, we also rely on sampling. Two prior interstellar visitors, Oumuamua and Borisov, define our expectations. With a sample size that's small, even one anomaly reshapes the curve. Perhaps the universe is filled with larger objects, and we've simply lacked the eyes to see them. The new Vera C. Rubin Observatory, soon to open its survey fully, may reveal that giants are not so rare after all. Or perhaps Atlas truly is unique. A fluke in cosmic statistics, a solitary traveller that breaks the rules. Astronomy often walks this edge between pattern and exception. We build models to describe the universe, then find phenomena that ignore them. Each anomaly forces us to widen our imagination. Once, comets were thought to be atmospheric vapours. Later, we learned they are icy relics from the solar system's birth. Now, we see visitors from beyond the sun's domain, carrying chemistry from distant stars. What might the next correction teach us? To look at Atlas statistically is to glimpse the vast machinery of cosmic evolution. Every number, every once in 10,000 years, contains stories of other stars, other collisions, other beginnings. It reminds us that randomness is only apparent when our perspective is small. From the galaxy's view, every improbable event is inevitable somewhere, sometime. Still, the coincidence of timing captures imagination. We, a young technological species, just now capable of mapping the sky in fine detail, happen to exist at the exact moment an interstellar giant crosses our neighbourhood. It feels like a cosmic wink, a gentle nudge saying, "You're watching at last." Perhaps that's the quiet gift of Atlas. It reminds us that observation is participation. The universe is not indifferent. It simply waits for us to notice. By counting improbabilities, we are measuring not the chaos of the cosmos, but our own expanding awareness of it. Even as probability charts suggest impossibility, the night sky keeps delivering surprises. Each discovery, each data point glowing faintly on a monitor, whispers that reality may be more generous than mathematics allows. And so, we continue to look up, one telescope at a time, one improbable visitor after another, humbled by the odds, yet blessed by their arrival. Before Atlas appeared, the story of interstellar visitors was small and quiet. Only two were known, and both slipped past quickly, leaving more questions than answers. They were the first hints that the void between stars is not empty, but seeded with remnants of distant creation. The first, Oumuamua, arrived in 2017, moving so fast that the sun's gravity barely curved its path. It shone without a coma or tail, an enigma of polished reflections and sudden accelerations that no one could fully explain. Some said it was a shard of rock or metal, flung from another star system by ancient planetary upheaval. Others wondered if it might be hollow, a wafer-thin light sail built by minds we could only imagine. 2 years later came Borisov, discovered by an amateur astronomer with a small telescope and a deep sense of curiosity. It was different, undeniably cometary, with a halo of gas and dust that looked like something from our own solar system's family. Its chemistry matched the familiar signatures of water, carbon dioxide and cyanides. In Borisov, we saw the ordinary stretched across interstellar distance, a comet from another sun behaving just like one of ours. Together, these two defined the boundaries of possibility. One was too strange to categorize, the other comfortably normal. They were the bookends of a new field, interstellar object astronomy, a discipline younger than a human generation. And then, in quiet July skies, Atlas appeared. At first, it was just a point of light beyond Jupiter, yet its brightness suggested something enormous. Its name carried a symmetry with the mythic Titan who held up the heavens, and that name now feels appropriate. It seems to hold the weight of a growing mystery. To compare them is to glimpse the diversity of what lies beyond. Oumuamua was small, barely 100 meters long, and Borisov perhaps half a kilometer. Both would fit comfortably inside a single crater of Atlas if it is truly several kilometers wide. The difference in scale is staggering. If you line them up by mass, Atlas outweighs them by thousands or even millions of times. In nature, large objects are rarer than small ones. This is the rule of power law distribution, the mathematical pattern that governs everything from asteroid sizes to earthquake energies. For every massive boulder ejected from a forming planet, there should be billions of pebbles and dust grains. To find the giant before we find the swarm seems backward, as if the universe skipped steps just to make a point. Astronomers consider the odds and hesitate. Maybe it's a detection bias. Smaller objects are dimmer, and we may simply miss them against the glitter of stars. Our telescopes favour the spectacular, not the subtle. Or maybe something else is at work, some process that favours the survival of large bodies over small ones as they drift between stars. Think of the galactic tide, the slow gravitational stirring from the Milky Way itself. Over millions of years, this force can erode orbits, scatter comets, and sweep away fragile bodies. The largest ones endure, while smaller fragments succumb to collisions or radiation. If that's true, then Atlas might be one of many survivors, ancient wanderers that have endured since the galaxy's youth. Each of these visitors carries a kind of biography written in orbit and chemistry. Oumuamua hinted at carbon-rich metals. Borisov smelled of water and cyanide. Together they proved that material from other suns resembles our own. Atlas continues that lineage, but larger, louder, more confounding. Every new discovery expands the known family tree of matter. When a comet crosses the solar wind, its gases spread like incense, and spectrographs read the faint rainbow lines that appear. In those lines are clues about the nursery it came from, its star's temperature, its early disk of dust, its first collisions. In this way, interstellar visitors are not intruders but couriers of memory. We might imagine them as seeds, drifting between the gardens of stars. Perhaps some carry organic molecules that once fell on fertile worlds, sparking chemistry. Perhaps others are relics of shattered planets, crusts of worlds long extinguished. Each one whispers of cosmic exchange, how stars give to one another through the slow commerce of gravity. Atlas continues that story but changes the tone. Where Oumuamua darted past in silence and Borisov shimmered like a textbook comet, Atlas lingers. It gives us time to breathe, to observe, to wonder. There's something almost human about this sequence of discoveries, like the early encounters of explorers finding new continents. The first sighting is confusion, the second brings recognition, and the third invites comprehension. Atlas stands at that threshold, a moment when the extraordinary begins to feel almost natural, and the natural begins to feel extraordinary. astrophysicists still debate what defines a true interstellar object. Some argue it must enter the solar system on a hyperbolic orbit that ensures it will leave again. Others prefer a broader definition, anything whose composition or motion reveals origins outside the sun's domain. Atlas fits both, at least for now, but its coming journey may challenge those lines once more. Through it all, we find ourselves at a quiet intersection of science and wonder. A decade ago, no one expected to see even one visitor from another star. Now, we've met 3, and if the pace continues, perhaps soon we will see dozens, then hundreds, until the idea of interstellar exchange becomes part of daily astronomy. The more we watch, the smaller the galaxy feels, not in size, but in connection. Stars are not isolated lights, they are neighbours sharing a common sea of drifting debris. Somewhere in that sea, Atlas took its first shape frozen by another dawn and began its long voyage toward ours. Now it moves through our realm, linking us to its birthplace across light years. Whatever it is, comet, rock, or crafted relic, it reminds us that the boundaries between systems are porous. The sky is not a wall but a bridge. Long before Atlas crossed Jupiter's orbit, it began to glow. Telescopes picked up its shimmer while it was still far from the sun, where sunlight is thin and the temperature is colder than liquid nitrogen. At that distance, most comets sleep, silent, dark, frozen, solid. Yet Atlas brightened, as if waking too early from a cosmic winter. Astronomers noticed it immediately. Its magnitude rose faster than models predicted, creating a mystery that still ripples through quiet observatories. Why would a comet shine so vividly in the outer reaches, where the light of the sun is too weak to stir vapour from ice? The first explanation was the simplest. Perhaps Atlas was unusually rich in volatile compounds, materials that evaporate at very low temperatures, such as carbon monoxide or carbon dioxide. These gases can sublimate even in the cold, releasing jets that scatter sunlight and make the object gleam. We've seen this before in distant comets, their faint halos shimmering like mist. But Atlas was different. Its brightness was too intense, its halo too large, its timing too early. At that distance beyond Jupiter, sunlight is 1/25 as strong as it is on Earth. It falls gently, more like a memory of warmth than the real thing. For Atlas to reflect so much light under those conditions, something unusual must have been happening on or beneath its surface. Some speculated about internal heat, perhaps from radioactive decay deep within, or friction from rotation. But comets are poor conductors. They rarely hold warmth long enough to glow from within. Others proposed that fine dust or frost newly exposed was scattering sunlight with uncommon efficiency. Even so, the glow remained strangely symmetrical, more like a steady lamp than a dusty cloud. Astronomers are cautious with language. They don't say impossible, only unlikely. Yet the light from Atlas challenged every known category. It seemed to defy the delicate balance of distance and energy that defines cometary behaviour. If we imagine standing near it, an impossible dream but a useful one, the landscape would appear ghostly pale. The nucleus would be covered in ice mixed with dark dust, pitted and cracked from eons of radiation. When the first sunlight touched it, tiny vents would open, sending faint streams into space. Each molecule of vapour would carry away a sliver of heat, a quiet exhalation from a body that has travelled longer than our species has existed. To see such a thing glowing of its own accord is to feel a strange intimacy with physics. It's as if the universe leaned closer, showing us that matter remembers light. Even frozen, it holds the potential for response. Astronomers compared its early brightness to known comets, Hale-Bopp, Hyakutake, Enkei, and found it brighter than any at similar distances. Hale-Bopp, one of the most spectacular comets of the 20th century, did not begin to shine so strongly until it was much closer. Atlas was breaking precedent quietly, like a note played before the music begins. Some wondered if the brightness came from structure rather than activity. A flat or reflective surface could amplify sunlight. A fractured crust could expose fresh ice that gleamed more efficiently. Perhaps we were seeing geometry other than chemistry. The difference is subtle but profound. One implies volatility, the other design. Still, most scientists favoured the natural. Space, after all, loves variety. There are comets that spin faster than models allow, asteroids that behave like comets, and icy bodies that switch personalities with each orbit. Atlas may simply belong to that restless family of outliers that remind us how incomplete our definitions remain. The glow also carried a deeper beauty. When telescopes captured long exposures, the object's light spread into a soft green hue, tinted by cyanide and diatomic carbon, molecules that fluoresce when touched by ultraviolet radiation. That gentle colour is familiar to comet watchers, but seeing it emerge so far away felt like witnessing life before dawn. It was as though the comet sensed the coming warmth and stirred, stretching in anticipation. Light behaves strangely in such distances. The faintest gleam must travel hundreds of millions of kilometres to reach our mirrors. Along the way, it passes through solar wind and interplanetary dust, scattering and fading. What finally reaches us is a ghost of the original glow, a signal so faint that only the most sensitive instruments can tease it out. Yet even through that veil, Atlas shone clearly, whispering through the static of space. This early light became a kind of omen among astronomers, a sign that this visitor might defy more than one expectation. As the weeks passed, and it brightened still further, predictions diverged. Some said it might disintegrate before reaching the sun, undone by its own exuberance. Others suggested it could survive and become a spectacle visible to the naked eye. Both scenarios carried romance, either a glorious self-destruction or a triumphant arrival. In the end, comets remind us of fragility. Their brightness is a slow surrender, a dance of evaporation that will someday leave them bare. What we see as beauty is in truth erosion, and yet there is comfort in that. The universe reveals its stories by letting them fade. Astrophysicists still debate why Atlas awakened so early. The theories range from exotic ices to structural fractures, from rotational heating to transient outbursts of trapped gas. None fit perfectly. Each explains a fragment of the story, but not the whole. That gap between observation and certainty is where wonder resides, the quiet space where science and imagination share the same breath. When we look up at that faint premature glow, we see not just a comet, but a mirror of curiosity itself, something stirred before the world was ready for it, shining anyway across the cold. There is a geometry to everything that orbits the sun. Planets, asteroids, comets, all of them trace paths close to a flat sheet of space called the ecliptic plane. It's the quiet stage on which our solar drama unfolds. The reason is ancient. When the sun was young, its swirling disk of dust and gas flattened as it spun, like a spinning plate of liquid light. Out of that thin plane, the planets condensed. Almost everything we know, every moon, every storm, every shadow, still obeys its slow geometry. And yet, Atlas, this visitor from beyond the sun's reach, moves almost perfectly along that same cosmic floor. Its inclination is less than 5 degrees, a narrow tilt that keeps it marching in line with the orbits of Earth, Venus and Mars. For something born under another star, that alignment is astonishing. The numbers tell a story of improbability. The odds that an interstellar object would wander into our system and happen to share our plane within 5 degrees is roughly 1 in 500. The galaxy is not short of directions. There are thousands of angles from which such an object could have entered. and yet Atlas came almost exactly aligned, as if choosing to glide where the planets drift. Astronomers plot its path with precision. Using ephemerides calculated from hundreds of observations, they chart how its orbit threads through our solar architecture like a needle passing through fabric. If you overlay that path on a diagram of planetary orbits, the match looks deliberate, so flat, so calm, so obedient to our geometry. But probability, as we've learned, is a soft language. Perhaps there is a natural explanation. Interstellar space is not random chaos, it has structure. The galactic disk itself, like our solar one, has a preferred orientation. Many star systems form within this shared galactic plane, and their debris tends to drift parallel to it. If both our solar system and Atlas's birthplace belong to the same cosmic sheet, then alignment may not be coincidence at all, but inheritance. Still, the nearness of the match feels intimate, like two strangers discovering they share the same handwriting. For Avi Loeb and others who ponder deeper possibilities, such coincidences invite contemplation. What if, they ask, we are seeing intention, not design in the human sense, but some quiet resonance of order we do not yet understand? The ecliptic itself is a thin realm, a kind of celestial equator dividing above from below. When we look at the zodiac, those constellations tracing the sun's annual path, we are gazing along that very plane. It is the line where the planets rise and set, where comets sweep long tails, where eclipses occur. To move within it is to move within the solar heartbeat. Atlas, then, travels the same corridor as the worlds. It passes through the same gravitational lanes that guide our planetary ballet. Each crossing means close brushes with invisible highways of dust and debris. In those regions, charged particles hum, and the magnetic fields of planets ripple faintly into the surrounding void. To glide through that structure unscathed requires exquisite timing. Astronomers sometimes speak of resonance, the gentle synchronization of orbits when gravitational tugs find rhythm. Jupiter, the great regulator, orchestrates much of that harmony. Many asteroids and comets follow orbits shaped by its influence. For Atlas to move within this plane, passing close to the paths of several planets, suggests it has entered that same resonant web. Whether by chance or by long drift, it is now part of the music. We could think of this alignment as the universe's form of choreography. Even chaos, given enough time, finds patterns that look like design. When particles move under gravity, they create natural harmonies, arcs and spirals that repeat, overlap and resolve. Atlas has simply joined that ancient rhythm, and by doing so it draws our gaze toward the quiet mathematics that keeps the cosmos balanced. Still, there's something uncanny about seeing an interstellar traveller adopt our geometry so precisely. It reminds us that the solar system is not a fortress, but an open current. The boundaries between ours and theirs dissolve in the slow blending of orbital planes. Each visitor carries traces of a shared galactic origin, the same dust and light folded into different shapes. The ecliptic is also our window to the universe, because it is the plane of planets. Most of our spacecraft travel within it. Voyagers, pioneers and New Horizons all sailed outward along its broad sheet. If we were to send a probe to chase Atlas, it would glide that same plane, surfing the sun's equatorial wind. Perhaps in some distant future that will happen. A small emissary from Earth chasing a visitor from another star, both sharing the same cosmic road. For now, we observe. Each night, telescopes trace Atlas's slow progress through constellations like Virgo and Libra, the same belt that defines the zodiac. To watch its path is to watch a story unfold in perfect alignment with our own. Perhaps it's just physics, or perhaps the universe has a sense of symmetry we don't yet grasp. Either way, there's a comfort in it. The same forces that shaped our planets now cradle this wanderer too. The same geometry that holds Earth steady in its orbit now guides a stranger across the same invisible floor. In that, we glimpse something profound. Order and randomness are not opposites. They are partners, each giving meaning to the other. Atlas moves as it must, drawn by gravity and coincidence alike, and in its path we see both our isolation and our belonging. The ecliptic plane, once thought to separate the solar system from the rest of space, may instead be a bridge, an invisible thread connecting countless worlds that share the same galactic heritage. And tonight, across that bridge, a silent traveller moves in harmony with us, tracing an arc of light that will soon disappear behind the sun. As Atlas drifts inward along that quiet ecliptic path, its story becomes one of proximity. The great planets wait like silent sentinels, each exerting its subtle pull. First Mars, then Venus, then Jupiter, 3 encounters written in advance by celestial mechanics, each improbably close, each defying the random shuffle of chance. The mathematics of orbital intersection is delicate. For any 2 bodies moving around the Sun, their paths can cross only if both timing and inclination align. To thread not 1, but 3 planetary lanes within a single approach, within a handful of months, is a rare coincidence. Astronomers ran simulations and found the odds astonishing, a probability near 1 in 20,000. Numbers like that make even cautious scientists pause, if only to appreciate how nature sometimes favours elegance over chaos. When we speak of close, we don't mean collision course danger. Space is vast. A close pass might still be millions of kilometres apart. Yet in orbital terms, such alignments matter. The gravitational influence of each planet adds a note to Atlas's motion, a subtle nudge that shapes its curve. Over time, these small harmonics can build into real change, deflections measured in degrees, shifts that can decide whether the visitor remains bound or escapes forever. Mars will see it first, though see is a generous word. The comet will pass through the Martian orbital corridor, far above the dusty red world itself. Still, the geometry aligns almost perfectly, and if robots there could lift their cameras at the right moment, they might glimpse a faint streak moving through their thin sky. Venus follows, its orbit pulling gently, a soft gravitational brush. Venus is nearly Earth's twin in mass and proximity to the Sun, and so its influence on an object like Atlas is modest but precise, just enough to whisper a change into its trajectory. Then comes Jupiter, the giant that rules the outer system. Its pull extends for hundreds of millions of kilometres, a gravitational tide that shapes everything from the asteroid belt to the comets of the Oort cloud. If any planet could rewrite Atlas's fate, it would be Jupiter. It's tempting to think of this sequence, Mars, Venus, Jupiter, as choreography, a cosmic waltz. The smaller worlds step first, the giant moves last, and through them all the interstellar traveller glides, indifferent yet somehow entwined in their rhythm. These alignments remind us that space is not empty. It's a field of overlapping influences, a quiet web where everything touches everything else, however faintly. In the centuries before precise mathematics, such encounters were read as omens. Ancient skywatchers believed the approach of comets foretold wars, floods, or the fall of kings. They didn't know about gravitational perturbation or orbital inclination. They only knew that the heavens were supposed to be steady, and when something wandered through them, it meant the order of things had changed. In a way, they were right. Every comet is change embodied, every visitor a reminder that the cosmos is alive with motion. Now we replace prophecy with probability, yet the awe remains. To see these alignments plotted against a star map is to glimpse design without a designer, the way numbers and distance alone can produce beauty. The planetary paths curve like threads of gold, and Atlas's orbit cuts through them in slow arcs. Somewhere deep in its icy core, molecules that formed around another star respond to sunlight that first touched Earth 4 minutes ago. The scale of connection is staggering. During these passes, gravitational tides may sculpt Atlas's path just enough to matter. A tug here, a deceleration there, perhaps a change of a few hundred meters per second, small on human terms, decisive on cosmic ones. Such adjustments could determine whether the Sun eventually binds it. In orbital mechanics, permanence is born of fractions. Astrophysicists run models of these interactions, using computers that simulate millions of possible futures. Most show Atlas continuing outward, its speed too high to remain. But a few rare scenarios, the slender tails of probability, show it slowing. Captured by solar gravity, looping back decades or centuries from now. The difference lies in timing and alignment, the very coincidences that already feel too perfect to ignore. When we think about alignment, we might also think about resonance between minds and moments. We, on this small planet, happen to exist at a time when technology allows us to witness such precision. That awareness itself is a form of resonance, a harmony between human curiosity and cosmic opportunity. The planets may not notice us, but we notice them, and in that attention lies meaning. Each close pass offers scientists a chance to measure subtle effects, how sunlight pushes against dust, how plasma tails react to planetary magnetospheres, how trajectories curve under compound gravity. These data teach us how to navigate our own system, how to guide spacecraft using the same physics that guides comets. In studying Atlas, we learn about ourselves, about motion, patience, and the art of reading silence. Perhaps the universe arranges these alignments simply because it can, because beauty is the natural consequence of enough time. Or perhaps such elegance is the rule, and randomness the exception. Either way, the pattern is there. 3 worlds, 1 wanderer, a dance of distance that no one choreographed yet everyone can see. As Atlas threads these lanes, its coma stretches in the sunlight, a faint green breath curling through planetary orbits that have endured for billions of years. It will leave traces, tiny grains of dust that may someday intersect Earth's path as meteors, flickering for an instant above sleeping fields. Each streak will be a reminder of this moment, when an interstellar traveller brushed past our world's invisible edges and continued on. For now, we can only watch, tracing the map of alignments, feeling the quiet pull of inevitability. Mars, Venus, Jupiter. 3 notes in a cosmic chord. Atlas moves through them not by will, but by the timeless music of gravity. And we, listening from our blue planet, can only breathe and marvel at how perfectly the melody plays. When coincidences begin to stack, even the calmest mind starts to wonder whether chance is the whole story. Astronomers are trained to accept randomness. The universe is big enough that rare events must happen somewhere, sometime. But every now and then, the numbers whisper something else, something that feels intentional, even if it isn't. Avi Loeb calls this the problem of loaded dice. If you roll a pair of dice once and they land on 6s, you smile. Twice, you raise an eyebrow. 10 times, you start checking the table. Atlas feels like that 10th roll. One improbable alignment might mean nothing. 2 or 3 begin to hum with pattern. Yet we have to remember how human perception works. Our brains are pattern-finding machines. We see shapes in clouds, faces on distant worlds, constellations in random scatterings of stars. It's what allowed our ancestors to navigate by the heavens, and also what makes us superstitious. When we look at Atlas's improbable geometry, the alignments, the timing, the quiet mass that resists perturbation, we must hold 2 truths at once: the wonder of coincidence and the discipline of restraint. In cosmic statistics, improbability does not equal impossibility. If the universe were truly random, then given enough time, everything that can happen will happen. Somewhere, a comet will align perfectly with planetary orbits. Somewhere, one will arrive behind the sun at the exact moment a civilization like ours happens to notice. We might simply be living in the somewhere where that alignment occurred. Still, probability carries its own poetry. 1 in 20,000 is not just a number, it's a measure of rarity, of how finely tuned the conditions must be for the event to exist. That fineness can feel like intention, like design, even when it emerges naturally from physics. Stars form in balanced chaos. Planets orbit in harmony born of violence. Beauty in the cosmos is often the residue of accidents. When we watch Atlas roll through these coincidences, we're really watching the interplay between chance and consequence. In orbital mechanics, every motion has a cause, every cause a lineage stretching back through time. Perhaps the chain that led Atlas here began before the sun existed, when a long-dead star flung this icy fragment into the galactic dark. Over millions of years, gravitational tides from passing systems nudged it, little by little, toward our corner of the galaxy. The path looks improbable only because we're seeing the final moment of a story written across eons, and yet, improbability still matters because it challenges our assumptions about normality. The early astronomers faced similar puzzles. When they first saw comets, they thought them divine messengers. Later, Newton showed that the same laws guiding planets guide comets too. The miraculous became mechanical, but the awe remained. Every era of science carries this rhythm: mystery, discovery, humility, repeat. Modern astrophysics still wrestles with that rhythm. We crave explanations that fit comfortably into equations, but some data points refuse to settle. Atlas is one of them. It glows too early, moves too smoothly, weighs too much. Each discrepancy can be explained away, but together they form a constellation of doubt. That constellation doesn't prove anything, but it keeps our curiosity alive, and that is its real purpose. In a way, rolling cosmic dice is what science does. Each observation is a throw. Most results come up ordinary, confirming what we already know. But sometimes, the universe rolls sixes, and those moments are where learning happens. They remind us that the map isn't complete, that the cosmos still has corners uncharted by logic. When we talk about odds, we're also talking about scale. 1 in 20,000 sounds astonishing, but the Milky Way alone contains hundreds of billions of stars. Multiply those odds by the number of chances, and rare events become routine on galactic scales. What is miraculous to us might be mundane to the universe. Perhaps the cosmos rolls so many dice that every outcome occurs somewhere, all at once, in endless quiet repetition. Still, Loeb's metaphor lingers because it captures something emotional as well as analytical. There's a thrill in the thought that we might be witnessing intent, that somewhere behind the statistics lies a will. Not necessarily alien intelligence, just the will of the universe to create patterns, to flirt with meaning. Even randomness, when stretched across infinity, begins to look like design. The physicist Richard Feynman once said that nature's imagination is greater than our own. That imagination expresses itself through symmetry and surprise, through coincidences that pull us to the edge of comprehension. Atlas's dance across our solar system feels like part of that imagination, an equation written in elegance, solved only by patience. As we reflect on these coincidences, it's easy to forget that we ourselves are products of improbability. Every atom in your body traces back to an unbroken chain of stellar births and deaths, each one statistically rare, each one necessary. The fact that you can sit here, listening to the story of a comet that shouldn't exist, is itself a miracle of probability. So when we speak of loaded dice, perhaps the dice are not loaded at all. Perhaps they're simply many. The cosmos rolls them endlessly, and once in a while, a combination catches our attention. We label it strange, we assign it meaning, and in that moment we glimpse the quiet conversation between chance and consciousness. Whether Atlas's coincidences are deliberate or natural may never be known. What matters is that they make us look deeper, think longer, feel the fabric of physics under our fingertips. Each anomaly is an invitation to wonder, and each wonder another small light against the dark. In the end, the question isn't whether the dice are fair, but whether we are paying attention. The universe keeps rolling, with or without us. Our task is simply to watch, to notice when the sixes line up, and to let curiosity guide us toward whatever truth lies beneath the numbers. October 29th waits like a quiet threshold. On that date, Atlas will vanish behind the sun, swallowed by the glare so completely that not a single telescope on Earth will see it. The astronomers call this solar conjunction, when the sun stands between Earth and a distant body and observation becomes impossible. To most people, it is a pause, a gap in data. But to Avi Loeb, it is an opportunity, a hidden window where an interstellar visitor could act unseen. Imagine the geometry of that moment. The sun at the centre, burning with ancient fusion. Earth trailing on one side of its orbit, Atlas on the opposite side rushing toward perihelion, the closest point of its curve. For days, maybe weeks, the object will be lost to direct observation. Even space telescopes, though free of daylight, struggle near the sun's radiance. The instruments saturate, their detectors flooded with photons. We can only infer what happens through prediction and afterthought, by comparing where Atlas was before and where it reappears after. Perihelion is where the laws of motion reach their climax. Here, speed and gravity lock in a delicate contest. The sun pulls hardest, the traveller moves fastest. In this region, a small change of velocity has enormous effect, a phenomenon known as the Oberth effect, named after the early rocketry pioneer Hermann Oberth. Spacecraft use it to gain momentum, firing engines when they are closest to a massive body. The short burst at high speed translates into a huge change in trajectory. The same principle works in reverse. A precise burn against motion can slow a craft enough for capture. Loeb calls this possibility a reverse Oberth maneuver. If Atlas were capable of propulsion, natural or otherwise, this is where it would use it. One calculated moment behind the sun, out of sight, could transform its path from open to closed, from a visitor's flyby to a resident's orbit. It wouldn't need to light visible engines or flare bright exhaust. A subtle change in momentum, only a few meters per second, could make the difference between departure and permanence. That idea is bold, perhaps even romantic, but it isn't beyond physics. Every spacecraft humanity has ever sent relies on such timing. The Voyagers used Jupiter's gravity to slingshot outward, gaining the speed to escape the sun entirely. The Parker Solar Probe dives perilously close to the sun, using Venus flybys to shed velocity until it can graze the corona itself. We already manipulate orbits this way. The thought that another intelligence might do so is not absurd, just unsettling. What makes this perihelion event haunting is its invisibility. The most crucial moment of Atlas's passage will happen behind a curtain of light. We'll only know afterward if something changed. When it reappears from the sun's far side in late November, astronomers will measure its new trajectory. If it still traces a hyperbolic path, an open curve, it will continue outward, a comet like any other, never to return. But if the path has softened into an ellipse, it means Atlas has stayed. There's a poetry in that uncertainty. Somewhere behind the solar blaze, an object from another star will decide its fate, and we will not be able to watch. It's a humbling reminder of how blind even our best technology can be. The sun that gives us life also blinds us, turning the heavens into silence for a while. For the teams tracking Atlas, preparation becomes everything. Before conjunction, they record position after position, refining models so precisely that even a deviation of a few hundred meters can be detected when it returns. They coordinate among observatories, ground-based, space-based, planetary missions, so that the moment it re-emerges, the telescopes will be waiting. The hope is to catch it early, measure its motion, and know if something extraordinary occurred while we were in the dark. In a sense, the sun itself acts as a veil in this drama, both literal and symbolic. It hides what we most wish to see, yet that concealment gives the story its tension. If the cosmos were entirely transparent, wonder might fade into familiarity. Mystery, even temporary, keeps curiosity alive. The days leading to October 29th will be filled with quiet anticipation. Astronomers will watch the data streams taper off as Atlas nears the sun. Nightly observations will stop. Charts will flatten into silence. For those who have followed this object for months, that silence will feel strange, like losing contact with a friend just before the ending of a story. But the universe has always moved behind veils. There are regions we can never observe directly. The core of the sun, the heart of black holes, the first instant of creation. We reconstruct them through traces, echoes, and mathematics. Atlas behind the sun is one more mystery of that kind. Something hidden, yet legible through its effects. And perhaps that is fitting. If there were an intelligence behind its motion, natural or artificial, it would understand concealment. Every species that learns to explore also learns to hide. To move behind the bright glare of its host star would be the perfect place for privacy, the quietest place in the solar system. Still, most likely, nothing so deliberate will occur. The odds remain that Atlas will pass unaltered, swept around the sun, and sent outward again. But the beauty of science is that even when nothing extraordinary happens, observation itself remains extraordinary. To watch a visitor from another system trace a path through ours, to predict its motion with equations and then see nature confirm them, that is its own kind of wonder. So we wait. We mark our calendars for the 29th day of October. We imagine the sun's light washing across Atlas's dark surface, heating it, shaping its tail, erasing it from our view, and while we cannot see, we imagine. Behind that golden blaze, a decision is written into orbital dynamics, a choice that may not be conscious but still feels alive. When the sun sets on that day, the sky will look unchanged. No flash, no sign, just the ordinary dusk of Earth, unaware of the drama unfolding on the far side of the light. But in observatories and quiet rooms, people will whisper the same thought. It's happening now. And for a moment, even science feels like prayer. When the calculations came in, they carried a quiet astonishment. For all its vapour and glow, Atlas was moving as if gravity alone guided it. No measurable wobble, no hint of a push from its own escaping gases. A comet's breath is usually uneven. When sunlight warms its frozen skin, pockets of ice erupt into vapour jets, and those jets act like tiny thrusters, nudging the body this way or that. Yet for Atlas, the path stayed pure and smooth, an almost perfect gravitational curve. To astrophysicists, that was both elegant and troubling. The data showed that its non-gravitational acceleration, the small extra motion caused by outgassing, was practically zero. The upper limit, no more than 15 meters per day squared, was astonishingly small. For comparison, most comets of similar brightness show 10 or even 100 times that drift. The conclusion seemed inescapable. Atlas was massive. Loeb's team did the math. If gas was streaming away at about 150 kilograms per second, and yet the orbit did not budge, the comet must weigh at least 33 billion tons. 33 billion. An almost unimaginable mass for an object only a few kilometers wide. The number implied a density far beyond what ice and dust alone could explain. It was like trying to push a mountain with a sigh. Such mass brings both stability and mystery. A heavy body ignores small disturbances, gliding through space with stubborn grace. You can almost picture it now. A dim sphere trailing a soft coma, unflinching as sunlight boils off its skin. Each puff of vapour drifts away like smoke from an ancient kiln, yet the kiln itself does not move. Its inertia is absolute, its patience infinite. For scientists, mass is not just a number, it's a signature. It tells the story of composition and structure. A comet made mostly of porous ice would be light and reactive. A denser mix of rock and metals would behave differently. When Atlas refused to flinch under the recoil of its own jets, the implication was clear. It was either huge, solid, or both. But the cosmos has a way of humbling certainty. Perhaps the mass estimate hides complexity. Maybe the gas flows are balanced, equal jets on opposite sides, cancelling each other's push. Or maybe the outgassing comes from deeper within, venting symmetrically through hidden fissures. It could even be that the dust veil we see exaggerates the comet's brightness, making it appear larger and heavier than it is. Still, Loeb's reasoning carries a kind of logic. A weight that great could explain why Atlas's trajectory appears immune to minor forces. It could also explain why its gravitational dance with Mars, Venus and Jupiter feels so exact. Heavy objects are harder to deflect, less sensitive to random nudges. In celestial mechanics, mass is momentum's memory. The heavier the traveller, the less it forgets where it's going. 33 billion tons. That figure echoes through imagination. If you compressed Mount Everest into a body 5 kilometers wide, the numbers would match. To hold that much matter together, the internal pressure must be immense. And yet, if it's truly that heavy, why is it not darker? Why does it shine so easily, scattering sunlight like powdered snow? Some astronomers propose that the coma hides a dense metallic heart, a nickel-iron core encased in lighter material. Others wonder if the estimate overstates reality, that what we're seeing is an illusion of scale and reflectivity. Either way, the data leave little room for comfort. Atlas sits near the upper limit of what a comet can be without fragmenting under its own gravity. The beauty of celestial dynamics is that mass is always measurable through motion. When an object moves exactly as Newton's laws predict, gravity alone is the sculptor. But when it strays, when small deviations appear, we glimpse forces we did not expect. That is why Atlas's obedience to pure gravity feels paradoxical. Its stillness, its refusal to deviate, is itself a kind of rebellion. A massive traveller like this carries secrets within. Deep below the coma, pressure keeps ices compressed, perhaps forming layers of exotic crystalline structures unseen in our solar system. At those depths, heat seeps slowly inward, and chemical reactions that began under another sun continue in silence. Molecules older than Earth shift and recombine, painting slow chemistry in darkness. The absence of measurable thrust also means that the object's spin might be gentle. Many comets tumble chaotically as jets fire from their surfaces, twisting them like irregular tops. Atlas, by contrast, may rotate slowly, smoothly, as if conserving some ancient balance. If true, that steadiness could explain the uniformity of its glow, the calm geometry of its coma. Astronomers have long used such stability to estimate size indirectly. A large, massive nucleus resists acceleration, while smaller bodies flutter. By combining brightness with inertia, we can infer scale, though never perfectly. Atlas seems to fall at the extreme, bright enough to suggest vastness, steady enough to demand it. Mass connects us to gravity, and gravity connects everything. It shapes not only the orbits of worlds but the stretch of time itself. In general relativity, massive bodies curve space-time, bending the flow of hours and minutes as surely as they bend light. If you could drift beside Atlas, its immense weight would tug ever so slightly on your sense of time, slowing your heartbeat by the tiniest fraction. You'd never notice, but the universe would. And so, As this comet sails toward the sun, its sheer weight becomes its anchor, a force that keeps it honest, predictable, dignified. Whatever gases pour from its flanks, whatever light it sheds, Atlas continues on the path gravity dictates, neither hurried nor delayed. It's strange to think that something moving at tens of kilometers per second can still feel motionless. Yet that's how Atlas behaves, a heavy ember gliding through an ocean of emptiness. Each time we measure its position, it is precisely where gravity says it should be. No panic, no protest, only momentum and silence. Perhaps that is what makes it so compelling. In a universe full of turbulence, this traveller's composure feels deliberate. Its calm is a statement written in celestial math saying, "I am too heavy for accident, too graceful for error." Whether that grace is natural or not, the numbers alone inspire a hush. If Atlas truly carries 33 billion tons of matter, yet glides so lightly through sunlight, then its mystery deepens into questions of shape and hollow space. Weight without resistance often means structure, shell rather than stone, a body that encloses more nothing than substance. The idea sounds fanciful, yet hollowness is not rare in the cosmos. Many worlds hide caverns of emptiness. The moon's Maria ring with echoes that suggest deep voids. Asteroids such as Itokawa and Bennu are not solid rocks, but rubble piles, loose collections of fragments held together only by gravity. Even comets in our own solar system often resemble sponges, riddled with pores and chambers where ancient ices hide from heat. So to call Atlas hollow is not to call it artificial. It might simply be exaggerated nature, a bubble of frozen time, expanded by internal gas crusted with dust. Still, the scale unsettles. A cavity kilometers wide could mean that its surface is a thin crust floating over an ocean of vapor or a honeycomb of tunnels. Radio measurements hint that the nucleus is larger than 5 kilometers, yet too light for its brightness, implying voids that make up much of its volume. The physics fits, but so does imagination. A hollow shell resists breaking because its stresses distribute evenly, allowing a fragile thing to travel intact across light years. Perhaps that is why this visitor survived while so many smaller fragments perished. To think of a comet as a vessel is tempting. A hollow form could protect volatile cargo from cosmic rays, much as a thermos protects liquid from cold. Inside such a shell, organic molecules might endure for eons, shielded until they meet another star's warmth. Some scientists speak of panspermia, the idea that life's chemistry drifts from system to system inside icy cocoons. Atlas, vast and enduring, could be one such arc, a frozen archive of carbon chains older than the Milky Way's spiral arms. Even if no life hides there, hollowness itself becomes poetic. The vacuum within a comet is a fragment of the interstellar void, sealed and carried like a relic. It's a pocket of true space preserved through motion, untouched by light since it first condensed. If we could peer inside, we might see dust grains older than our sun, still whispering the signature of their birth nebula. Astronomers test such possibilities through indirect light. As Atlas turns, variations in brightness, called light curves, reveal shape and spin. So far, its light changes slowly, implying a round, stable form rather than a jagged chunk. But within that steadiness lies room for imagination. A nearly spherical object with an unexpectedly low density could hide an internal cavity, a globe of emptiness encased in frost. To some, the idea evokes human structures, domes, hulls, chambers. Loeb sometimes allows the analogy but speaks of it as hypothesis, not fantasy. The line between natural geometry and design remains wide. Yet the mere act of considering it expands science's vocabulary of curiosity. We learn not by declaring what a thing must be, but by asking how it could be otherwise. Inside a hollow comet, pressure behaves strangely. When sunlight warms the interior walls, Sublimated gases may circulate like slow winds, equalizing temperature and preventing violent jets. That would explain why Atlas's outgassing seems balanced, why no measurable thrust disturbs its course. Its hollowness could be self-regulating, a natural engineering that steadies flight. Think of the Rosetta mission's findings at Comet 67P. That smaller nucleus contained voids where gases built up and escaped through vents, carving smooth pits. Now scale that up by orders of magnitude across an object miles wide and older than Earth's continents. The internal geography of Atlas could be a cathedral of ice, resonating softly as the sun's heat moves through it. Light would behave differently inside such caverns. It would scatter blue and green, refracting through frozen crystals like lantern beams in fog. The temperature gradient, outer surface at 100 Kelvin, inner walls perhaps tens warmer, might create faint electrical currents, static whispers echoing in the dark. It is strange to think that physics, left alone for millions of years, can build cathedrals more intricate than art. If hollowness defines Atlas, then it also defines us. The atoms of our bodies are mostly space. The distances between nuclei and electrons dwarf the particles themselves. On every scale, the universe builds strength from emptiness. Stars survive by balancing pressure against gravity, galaxies by balancing mass against expansion, consciousness by balancing wonder against knowledge. The void is not absence, it is structure. So when scientists model Atlas as potentially hollow, they are not inventing miracles. They are recognizing a pattern. The cosmos repeats itself, from atomic shells to planetary rings, from soap bubbles to nebulae. Each form holds a boundary where matter ends and space begins, and at that boundary beauty happens. If Atlas is a shell, then it is a cosmic echo, a sphere drawn from dust and silence, now illuminated by our sun for the briefest time. When it swings near perihelion, that sunlight may reach deep into its hollows, warming cavities untouched for eons. Jets may awaken, but their push will cancel, keeping the giant steady as ever. Its brightness may pulse slightly, a slow heartbeat under layers of frost. We may never send a probe there. The distances and speeds make such missions dreams for another century. Yet telescopes and spectrographs can still listen. They will record how light scatters, how infrared signatures change, how molecules escape. Every spectrum line, every shift, will tell us a little more about the emptiness inside. Whether solid or hollow, natural or shaped by accident, Atlas reminds us that space is not uniform. Each traveller carries its own architecture, a memory of forces that sculpted it. In its silence, we hear the echo of the very process that built stars, planets, and perhaps ourselves. The shaping of substance around a core of nothing. To call it a vessel may be poetic, but poetry often comes closest to truth. Somewhere out there, behind the sun, a hollow traveller glides through light, ancient and self-contained, a reminder that sometimes what endures longest is not the material, but the space it protects. Each new measurement of Atlas folds another thread into a web that seems too intricate for coincidence. The alignments, the weight, the timing, none impossible on their own, but together they weave a pattern that glows faintly with suggestion. The scientist must name that glow what it is: curiosity, not proof. Yet curiosity is what keeps the species looking up. Every orbit is an answer to a question that gravity once asked. Objects move the way they must, responding to invisible pulls, to balances of energy and mass. Atlas should be no different, and still, there it is. Too heavy to nudge, too neatly aligned with our planetary plane, too timely in its arrival. Each feature could have a natural cause, but when they appear together they stir something deeper than logic. Astrophysicists live in that in-between. They know the universe permits coincidences because its stage is vast and repetition is inevitable. they also know that coincidences cluster around the edges of discovery. When early astronomers noticed that planets wandered differently from stars, they saw pattern in what looked like randomness. From that realization came the first laws of motion. Perhaps Atlas's improbable combination is another invitation to learn what pattern we've missed. The way a comet story forms is through accumulation. One anomaly becomes two, then three, until the whole record hums with a rhythm we can't ignore. The mind starts to connect dots that may not connect at all. Loeb's team calls this the architecture of improbability, the way separate facts seem to lean toward one another until they almost touch. And so the conversation continues. On one side, those who insist that chance is plenty. On the other, those who say the odds themselves are the message. Both views require faith, though in different languages. The skeptic trusts statistics, the dreamer trusts intuition. The truth most likely sits quietly between them, waiting for better instruments. Pattern has always been a double-edged tool. We used it to map constellations and also to imagine gods inside them, yet even illusions can teach. When we draw meaning across the stars, we reveal our own shape of thought. Perhaps the reason Atlas feels significant is not what it is, but what it mirrors in us. A need to see coherence in a universe that otherwise drifts without narrative. Still, the coincidences deserve attention. Its path threads through planetary orbits with almost mathematical grace. Its brightness rose when models said it should sleep. Its mass refused to betray even the faintest push of gas. If you listed those facts separately, each would be unremarkable. Together, they form a chord that resonates longer than chance usually allows. There is a term in statistics called the birthday paradox. It shows that coincidences become common when the number of possibilities grows large. In a room of only 23 people, the odds that two share a birthday are already better than even. The cosmos is a room of uncountable billions. Somewhere in that crowd, coincidences are bound to meet. But what matters is that we notice them. Observation turns random overlap into story. When we track Atlas night after night, comparing its behavior with prediction, we're doing more than science. We're participating in an old ritual, the practice of wonder shaped by patience. Each confirmed measurement tightens the web, replacing imagination with evidence. Each uncertainty keeps imagination alive. The two together form the heartbeat of discovery. Perhaps years from now, new data will flatten the mystery. The alignment will prove typical, the mass overestimated, the brightness explained by dust grains of the perfect size. If that happens, the wonder will not vanish. The beauty of Atlas is not that it might be extraordinary, but that it made us look close enough to find out. Until then, the web of improbabilities glitters like frost on a telescope dome. We see connections where the equations blur, and for a moment the distance between natural and intentional feels thin. Even if every strand dissolves under scrutiny, the shimmer itself was real. That shimmer is why astronomers keep building better mirrors, why data analysts sit through long nights of numbers, why poets still write about comets. The cosmos gives us puzzles not to solve them perfectly, but to remember that perfection exists only in the asking. Atlas, with its chain of coincidences, has become a mirror for that process. Whether it is a mere heap of ancient ice or something stranger, it invites us to balance skepticism with awe. To admit that we don't know is not failure, it is fidelity to truth. The web of improbabilities is not a trap, it is a net we cast into the dark, hoping to pull back a little more understanding. Somewhere tonight that heavy, hollow traveller still glides through sunlight, indifferent to our debates. It rolls its slow orbit, neither confirming nor denying anything. Perhaps that is the final lesson, that meaning, like gravity, emerges from relationship. The patterns we see in Atlas may be real, or they may be the reflection of our own longing for connection. Either way, they bind us to the sky. In the spring and summer months of observation, the images began to show something stranger still. When the Hubble Space Telescope fixed its gaze on Atlas, the familiar geometry of a comet seemed reversed. Instead of streaming a tail behind it, the brightest glow burned ahead of its motion, a soft lamp shining into the dark. For a few nights it was as if the traveller carried its own headlight through the void. No one could quite agree on what they were seeing. A telescope is both eye and translator. Its images are shaped by optics, filters, and timing. A miscalibration could create illusions, a trick of phase angle, or a scattering of sunlight off dust in ways the camera wasn't designed to capture. But even after corrections, the anomaly remained. The coma of Atlas was brightest in the direction of travel, not behind. Normally, a comet's tail forms when the sun's heat lifts gases and dust from its surface. Radiation pressure and solar wind then sweep that material away, always pushing it roughly opposite the sun. That's why tails point outward, like arrows of light showing where the solar breeze flows. But Atlas seemed to glow into the oncoming dark, its light facing forward, its dust behaving against expectation. At first, scientists thought the image orientation might be flipped. When you study the sky, north and south are not fixed. Cameras invert and rotate their frames. Yet repeated observations confirm the same result: a persistent brightness in front of the nucleus. It wasn't the dramatic flare of propulsion, nothing so cinematic, but a consistent asymmetry, subtle and deliberate looking, as if something about the comet's surface or spin favoured illumination ahead. The simplest theory was geometry. Perhaps a jet on the sunward side produced a cone of dust that, from our perspective, seemed to lead the motion. If Atlas's rotation aligned that jet forward along its trajectory, the apparent headlight could be an illusion of angle and time delay. Light scattering through a dense coma can play tricks. The human eye, and even digital sensors, translate three-dimensional halos into flat portraits, losing context in the process. Still, the image haunted many who saw it. To see a glow where a tail should be feels like seeing reflection turned inside out, a comet contradicting its own physics. In that reversal, imagination finds room to stretch. Was it some surface property that reflected light forward, like retro-reflective fabric on a road sign? Or perhaps particles of an unusual composition, flat, mirror-like grains, oriented magnetically in ways ordinary dust is not. Astronomers are cautious, but the mind of wonder is not easily fenced. Loeb and others entertained every mundane cause first: dust alignment by magnetic fields, ion tails reacting to the heliospheric current sheet, even small imaging artifacts from Hubble's point spread function. And yet, when combined with Atlas's other peculiarities, the mass, the brightness, the improbable orbit, the forward glow refused to rest comfortably among coincidences. To the lay observer, the sight carried poetry. In long exposures, the leading light appeared soft, greenish-white, diffused like breath against glass. The surrounding coma swelled evenly around the nucleus, but that single forward lobe shimmered brighter, as if the traveller looked where it was going. It was easy to imagine a lantern, a search beam, a gaze. But perhaps the explanation lies deeper in the physics of dust. The sun's radiation doesn't push on all grains equally. Smaller particles, mere microns across, respond strongly, flying backward to form the classic tail. Larger grains, heavier and slower, linger near the nucleus or even drift slightly forward under gravity before the solar wind claims them. If Atlas's outgassing favoured such grains, dense, metallic or carbon-coated, they might create a forward-skewed haze, a statistical artifact that human eyes read as intention. The debate itself reveals something gentle about science. It is a discipline of patience. Each new mystery first stirs a storm of speculation, then settles into careful study. Over time, data replaces drama. The headlight becomes a plume, the plume a scattering function, the function a paper quietly archived. Yet for those brief months before consensus, the world gets to wonder. To imagine a light travelling ahead of a comet is to invert the usual order of things. Normally, tails symbolise the past, the trail of what's been burned away. A forward glow feels like the opposite, as if the object were lighting the path before it, guiding itself toward the sun. The metaphor is irresistible. Perhaps that is why this detail, even if purely physical, captured so many hearts. In the grander view, the anomaly fits a pattern that nature loves: a symmetry. Nothing in the cosmos is perfectly balanced. Galaxies spin faster on one side, nebulae bloom unevenly, magnetic poles drift. Even light itself bends differently through dust depending on angle and grain. Perfection is not the rule, but the illusion. Irregularity is the signature of reality. Atlas's glow, then, might simply be another example of how the universe writes character into its creations. As Hubble continued its vigil, later images began to show a more conventional shape. The tail lengthened, stretching outward from the sun, the coma smoothing into the textbook curve. Whatever caused the forward light had passed. Perhaps it was a transient event, a sudden venting, a flare of chemistry that balanced itself again. The headlight faded back into the normal, leaving behind only a few frames of strange beauty. But those frames endure, shared across observatories and online archives, reminders of how easily expectation can be turned. For a short while, an interstellar traveller seemed to lead itself through space, a flicker of mystery in an already improbable story. And maybe that is enough. Science doesn't need every riddle to become revelation. Sometimes it just asks us to look twice, to notice how a single photon can bend our assumptions. Even when the explanation is mundane, the moment of seeing is magic. Atlas's forward glow was that kind of moment, a brief inversion of cosmic order that made everyone pause and remember that the sky, no matter how well mapped, still keeps surprises hidden in plain light. By the time autumn deepened and the comet neared the warmth of the inner system, that strange forward glow had softened into a familiar tail. The new images showed the expected shape, sunlight and wind pressing dust backward, the comet's body now trailing a luminous veil that stretched for millions of kilometres. The spectacle was comforting, almost like seeing an old friend return to predictable behaviour after a period of wildness. And yet, some of the scientists who had watched Atlas for months couldn't quite let go of what had come before. The change from anomalous light to ordinary tail felt too neat, as if a mask had slipped back into place. They began to wonder whether the comet's early oddities had simply been hidden beneath the ice, some deeper structure that only revealed itself when the warming sun reached the right depth. It would not be the first time a comet surprised its watchers. In 2015, the European Space Agency's Rosetta mission found that the nucleus of Comet 67P had a layered crust that concealed pockets of gas. When those layers cracked, sudden plumes erupted, briefly altering the comet's brightness and shape. Later, everything seemed calm again. The surface cooled and the jets stopped. What Rosetta saw up close, astronomers now saw from afar in Atlas, the pulse and retreat of buried forces. For months, the data suggested a steady brightening curve. Then, near the point of maximum light, Atlas dimmed for a few days before flaring again. That dip could have meant a fracture, surface material breaking away, exposing new ice beneath. The process is both ordinary and violent. When trapped gases find a path to escape, they carve caverns wider than city blocks. As those hollows collapse, the nucleus reshapes itself. From Earth, we only see the flicker, the breathing of a living geometry. Some observers began calling that phase the awakening. The word caught on not because anyone believed the object alive, but because the metaphor fit the rhythm. Atlas was stirring, turning slowly toward the sun like something that had slept too long in the cold. Its surface chemistry supported the image. Sudden bursts of cyanogen and carbon monoxide followed by long quiet stretches, as if exhalations came in cycles. To describe such things is to walk the line between science and poetry. The data give us numbers, but the experience gives us wonder. Every brightness curve carries emotion because it represents transformation, the moment when an inert relic becomes a moving fountain of light. Atlas's new tail glowed pale green against the black, a colour that always seems alive even when it is purely mechanical fluorescence. Green light in comets comes mainly from diatomic carbon, two carbon atoms bound loosely together. When ultraviolet radiation strikes them, they emit that ghostly emerald hue. The molecules survive only a few hundred kilometres from the nucleus before sunlight tears them apart, so the glow always clings close to the core. It is the colour of impermanence, the visual signature of molecules dying beautifully in the light. Perhaps that is why the notion of a mask resonated so strongly. The comet's outer crust, blackened by eons of cosmic rays, had hidden all that chemistry until now. When it thawed, the inner layers bloomed into colour. The disguise of darkness melted away to reveal the bright machinery beneath. Seen this way, the comet's awakening was simply exposure, sunlight peeling back the armour of distance, showing what was always there. Theories multiplied about what lay below the surface. Was the structure homogeneous, or was it stratified like a planet's crust? Did the earlier glow come from a jet venting through a fissure, or from deeper materials resonating with solar particles? No single model fit every observation. The conversation itself became the point, a community of minds tracing the fine line between pattern and coincidence. For those following from home, the change was visible even through small telescopes. The coma, once round and compact, now stretched visibly. Photographs taken weeks apart showed its tail lengthening, the forward light dispersing into the trailing plume. What had once looked like a secret signal now looked like nature resuming its script. The beauty of that transition lay in its humility, mystery dissolving into ordinary physics, and the ordinary proving no less sublime. If we could stand nearby, on some silent probe hovering a few kilometres away, the view would be breathtaking. Streams of gas would rise from fissures, curling in slow spirals under microgravity. Ice grains would tumble outward, catching sunlight like floating mirrors. Behind them, the dark body of Atlas would glisten with a thin frost, pocked and glittering like the surface of an old glacier. Nothing dramatic, nothing explosive, just the steady breath of sublimation, the soundless rhythm of heat meeting cold. In that scene, we might finally understand why scientists speak of comets as time capsules. Each eruption exposes layers untouched since the birth of the parent star. The chemistry there remembers a younger galaxy, one filled with dust from supernovas and molecular clouds rich in carbon. Atlas carries that memory still, and its bright tale is merely the story retold through sunlight. When the forward glow finally faded, some observers felt a quiet relief. The mystery had not vanished, but it had matured into familiarity. We could explain much of what we saw, and what we couldn't no longer frightened us. It was enough to know that the universe still had tricks to play. Every comet is a cycle of concealment and revelation. Atlas simply made that cycle visible in fast motion. The hidden face of its approach, the unveiling near perihelion, the mask restored as the tail took over. Whether anything extraordinary lay beneath doesn't matter as much as what it taught us. That even the most routine physics, when witnessed closely, can feel like rebirth. The next time we look up and see a comet glowing in the twilight, we might remember this one. Its green shimmer, its strange direction of light, its graceful return to normal, all reminders that discovery is often just recognition in disguise. The cosmos hides its truths behind simple patterns, waiting for us to notice when something old behaves as if new. The transformation of Atlas reached a point where colour itself became a story. When its brightness deepened into an unmistakable green, the scientific community grew quiet with curiosity. That hue, delicate and unearthly, is one of the rarest tones nature paints across the void. It means chemistry, molecules awakening under sunlight after ages of silence. Every comet has its signature colour. Most appear white or bluish, the reflections of ice crystals and scattering dust. But sometimes, when the right molecules meet the right light, a glow of emerald spreads through the coma. For Atlas, the effect was pronounced. It came suddenly, a soft mist of green that seemed to bloom outward from the nucleus as it approached the sun. At first, the cause was predictable. The glow likely came from C2, or diatomic carbon, which fluoresces in sunlight. Yet something about the timing made it remarkable. The emission began farther from the sun than expected, at a distance where ultraviolet light should have been too weak to excite such molecules. It was as though a buried layer of volatile material had cracked open earlier than physics allows. Astronomers turned their spectrographs to the comet, analysing the faint rainbow lines in its light. The pattern told of carbon, cyanides, and water ice. But the relative strengths were unusual. The carbon bands dominated. The familiar hydrogen and oxygen lines were faint. Atlas seemed rich in the building blocks of organic chemistry, but poor in the ordinary ices that define most comets. That imbalance carried implications beyond colour. It hinted at an origin older or stranger than our solar nursery. Green then became more than a shade. It became a message from the molecules themselves. Carbon, freed from its frozen prisons, was speaking in light. Each photon emitted by C2 lasts only a billionth of a second, but multiplied across trillions of atoms, the combined shimmer reached Earth like a cosmic sigh. To human eyes, that shimmer feels alive. It's easy to see why cultures once called green comets omens of rebirth or visitation. The colour of spring on Earth is also the colour of awakening in the sky. Some chemists suggested that the fluorescence could indicate layered composition. Beneath Atlas's outer crust, where more stable ices of water and carbon dioxide dominated, there may lie a core enriched with carbon-heavy compounds, tar-like residues from interstellar chemistry. As sunlight penetrated deeper, it would vaporize those materials, producing the green sheen. The effect would last only until the layer burned away, fading as the comet's skin peeled open, a living metaphor for transience. Others proposed that the green hue was amplified by resonance fluorescence, a feedback loop where photons from one part of the coma excite neighbouring molecules, causing waves of light to cascade outward. If so, the colour might have spread like a slow aurora, a luminous ripple across thousands of kilometres of gas. The physics behind it is complex but beautiful. Ultraviolet light absorbed by one carbon molecule can bounce to another, triggering emission in a chain reaction of glowing chemistry. To Loeb and the observers who favoured broader possibilities, the green awakening symbolised something more philosophical. The comet seemed to reach a threshold, a point where it changed from passive to active, from reflecting light to generating it. In purely physical terms, that meant the transition from inert to reactive molecules, but in poetic terms, it looked like intention, an object crossing from silence into expression. We know better than to anthropomorphize, yet science itself often borrows the language of life because it feels appropriate. We say stars are born, comets die, galaxies collide. These are metaphors, but they point toward truth. The processes that shape lifeless matter and those that animate living cells are variations of the same chemistry. Carbon binds, releases, reforms, energy flows, time changes phase. Atlas's green light is a microcosm of that cosmic continuity, the same chemistry that colours a leaf now shining in the dark between planets. When seen through long exposure, the green aura enveloped the entire coma, fading gradually into black. Amateur astronomers described it as an underwater glow, like sunlight in deep seas. It gave the impression of transparency, as if one could swim through it. Even professional scientists felt its spell. Many admitted later that it was among the most beautiful comet images they had ever recorded. Yet beneath that beauty lurked an analytical puzzle. The relative abundance of carbon compared to water, roughly 8-1, was unlike anything in the catalogue of known comets. In most, water dominates by far. The ratio suggested that Atlas either formed in an unusually dry region of its home system or had lost much of its water during interstellar travel. Both explanations carry deep consequences. The first means that planetary systems can produce carbon-heavy debris. The second, that interstellar radiation can sculpt matter into new forms over eons. Either way, the comet is a time capsule of alien chemistry. In laboratories on Earth, scientists replicate such conditions in vacuum chambers, bombarding frozen mixtures with ultraviolet light to watch new molecules form. Out of that light-dark interplay come amino acid precursors, alcohols, simple sugars, molecules that, given time and warmth, can assemble into life's first structures. So when Atlas glows green, we are in a sense watching prebiotic chemistry reenact itself on a celestial scale. A reminder that life's ingredients are not rare, only waiting for their stage. Astrophysicists still debate how to classify such emissions, natural variation or anomaly, but for storytellers, and for those who lie awake under the stars, the meaning is simpler. The green light is the colour of continuation. It tells us that the elements are still restless, still transforming, still reaching across the gulf of time to speak in photons. As Atlas drifts closer to the sun, that glow will brighten and then fade, consumed by the very energy that made it visible. What begins as awakening always ends in evaporation, yet the memory lingers. In every image captured from Earth, that green aura hovers like a whisper, saying, even the coldest fragments remember how to shine when touched by light. The spectra coming from Atlas grew stranger the closer it drew to the sun. Behind the beauty of that green halo, scientists began to detect ratios that made little sense, particularly the overwhelming abundance of carbon dioxide compared to water ice. In most comets, water dominates, releasing vapour as soon as sunlight touches it. Atlas, however, seemed ruled by gas that, on Earth, fills our breath and our atmosphere. The measured ratio, roughly 8 parts carbon dioxide to 1 part water, stood apart from everything we had catalogued before. That number reshaped how astronomers thought about its origins. To produce such a composition, the object must have formed in an environment rich in carbon and relatively poor in oxygen. Our own solar nebula, in its early days, created plenty of water-rich comets. Beyond the frost line, temperatures dropped enough for hydrogen and oxygen to pair easily into ice. For Atlas to show the opposite balance, its nursery must have been colder still, or exposed to radiation that stripped water away before the comet ever left home. Spectroscopy is both art and patience. The faint light collected by instruments like the James Webb Space Telescope travels for hours through mirrors and filters before scientists break it into spectral lines, each one a barcode of atoms. In Atlas's case, those lines told a story of exotic chemistry. Methane and ethane appeared in weaker traces than expected, and the carbon monoxide peak was sharp, suggesting an interior where frozen gases lie close to the surface. That closeness hints at rapid evolution, a comet that did not linger long in its birth system before being thrown into interstellar exile. If that's true, then Atlas is young, not by human measures but in cosmic terms. A few 100 million years since its formation perhaps, carrying unweathered material from the outer shell of a distant protoplanetary disk. It may come from a system whose star differs from ours, perhaps one slightly cooler, its planetary belts more carbon-heavy. Every detail invites the imagination to travel backward, a dust ring around another sun, collisions birthing icy fragments, one of which escapes and drifts for eons through the galaxy, until at last it meets our light. The 8-to-1 ratio fascinates not only because it is unusual, but because it feels intentional in its precision. Nature rarely builds exactness without a reason. Some astrophysicists compared the data to the chemistry found in carbonaceous chondrite meteorites, which also show enrichment in carbon compounds. But even those rocks, the oldest known relics of the early solar system, do not reach such disparity between carbon and water. Atlas seemed purer, stripped to essence, a body built of carbon and cold. One theory suggests that it may be a fragment of a once larger planetesimal, perhaps the mantle of a carbon-rich world whose crust broke apart under gravitational tides. Another idea posits that interstellar radiation over millions of years selectively eroded lighter ices, leaving denser carbon dioxide frozen deep within. The outer layers of water would have sublimated away in the dark, atom by atom, until only the heavier compounds remained. What we see now could be the final sculpture of cosmic erosion, a core laid bare by time. Whatever the process, the result is a comet that behaves differently from any we've known. Its coma thickens with heavy molecules, its tail carries dust that glows green but moves sluggishly. Radiation pressure, which normally pushes lighter dust outward, struggles against the weight of carbon dioxide frost. The tail curls more gently, a languid plume rather than a jet. In that slow motion there is grace, the dignity of ancient matter rediscovering sunlight. The Webb telescope captured infrared signatures that deepened the mystery. In the long wavelengths, Atlas shimmered with unexpected warmth, as if it absorbed more sunlight than its colour should allow. Some speculated about surface texture, microcrystals acting as tiny lenses, focusing heat inward. Others pointed to a crust of dark tholins, complex organic polymers that form when ultraviolet light bakes carbon compounds over millennia. Those tholins, found on outer solar system bodies like Pluto and Triton, are reddish-brown in visible light but absorb strongly in infrared, explaining the heat. If Atlas's skin is covered in such material, then it is not only foreign, it is a cousin to the farthest edges of our own planetary frontier. This chemical difference matters for more than curiosity. Carbon dioxide sublimates at lower temperatures than water, meaning that Atlas's activity begins earlier and farther from the Sun. That explains its premature brightness beyond Jupiter, its early awakening that puzzled observers months ago. The composition ties the phenomena together: the light, the mass, the timing, even the forward glow. What seemed at first a chain of coincidences may instead be the predictable behaviour of a carbon-borne comet under unfamiliar sunlight, and yet knowledge does not diminish wonder, it only gives it context. To know that green light comes from molecules torn apart by ultraviolet energy is no less beautiful than imagining it as an aura of intention. The truth is more intricate. Radiation, chemistry, distance, and time all playing their parts in a slow performance. Atlas, illuminated, becomes a map of cosmic chemistry. In its spectral lines we see the echoes of creation itself, how carbon learned to bond, how matter learned to glow. Still, there remains an unease among researchers, a sense that something is missing from the equations. The precise ratios, the smoothness of the coma, the absence of chaotic jets, all these resist the random textures of ordinary comets. It is as though the object has been refined, its surface and composition simplified over ages into a kind of minimalism. Whether that minimalism is accident or artifact, no one can yet say. In the end, the data remind us how alien even natural objects can be. The universe does not owe us familiarity. It produces worlds of diamond rain, moons of methane, comets of carbon. Atlas joins that gallery, a singular sculpture of ice and fire, its green heart whispering across millions of kilometers that chemistry itself can be a form of art. The spectrographs still record its fading song each night. Every photon they catch adds another note to the score. Carbon dioxide dominant, water subdued, a rhythm of contrasts. if music could exist in vacuum, perhaps this is how it would sound, one element singing louder than the rest, a solo against the backdrop of starlight. And as always, we listen, translating colour into composition and composition into story, until the line between science and reverence dissolves into quiet. Avi Loeb once said that the universe rewards those who measure their curiosity. Out of that conviction came a simple but daring idea, a kind of compass for wonder that he called the Loeb scale. It is not a hierarchy of belief, but a ladder of possibility. Each rung measures how confidently we can say that a visitor from the stars is natural, or perhaps made. 0 marks a stone, pure and simple, a fragment of cosmic geology following the dictates of physics. 10 marks something no physics can explain, an artifact of mind. Between them lies the grey ocean where most mysteries drift. On this scale, Atlas might hover around the middle, not because we can prove intention, but because we cannot yet rule it out. Loeb designed his scale not as an answer but as a discipline, a reminder that uncertainty deserves structure. Just as seismologists rank earthquakes by magnitude or astronomers chart stars by spectral class, he believed we should catalogue anomalies with the same calm precision. A score is not belief. It is attention formalised. The idea of quantifying wonder may sound cold, but in practice it brings humility. To place a number on possibility forces us to confront our ignorance honestly. If Atlas scores a 5, that means the data invite but do not compel the extraordinary. It means the door is half open, the light slanting through but not blinding. That posture, curious but cautious, is the essence of scientific listening. Astronomy has long used scales to navigate the unknown. The Torino scale classifies asteroid impact risks. The Kardashev scale imagines the power of hypothetical civilizations, from those harnessing their planet's energy to those mastering galaxies. Loeb's proposal sits quietly among them, not predicting doom or grandeur, only discipline. It reminds us that probability is a spectrum, not a verdict. Each interstellar visitor, he suggests, deserves a score, however provisional. A 1 or 2 would describe a comet behaving as expected, tail aligned, chemistry ordinary, trajectory unremarkable. A 4 or 5 would signal multiple anomalies, statistically improbable alignments, or compositions outside known ranges. Anything above 7 would require undeniable signatures of technology, self-propelled motion, radio emissions, or geometry too precise for nature. By keeping such a scale, scientists could allocate their limited attention wisely. When a new object crosses into our sky, the number would guide which telescopes watch, which missions pivot, which data deserve midnight analysis. In principle, this sounds simple. In practice, it challenges human psychology. We are creatures of pattern and bias. The urge to dismiss or to sensationalize often outruns evidence. Loeb's system aims to slow that reflex. It says, measure first, marvel second. It creates room for disagreement without derision. If one researcher gives Atlas a 6 and another a 3, they can discuss why. The quality of data, the assumptions of models, the uncertainties in brightness or mass. The debate becomes numerical, not personal, anchored to shared evidence. We already grade the sky in other ways. The Bortle scale, for instance, measures darkness, how well you can see the Milky Way from your location. On a scale of 1 to 9, 1 means pristine wilderness, 9 means the glare of a city. Amateur astronomers know the comfort of having a number for something otherwise subjective. Loeb's approach is similar but grander. Not the brightness of the night, but the brightness of possibility. To some, that ambition feels unnecessary. Why quantify mystery? But others find reassurance in it, a reminder that even wonder can be organised. Science thrives on such frameworks. The Drake equation once tried to estimate the number of communicative civilizations in the galaxy, not to produce an answer, but to reveal the parameters of ignorance. Each term, star formation rate, habitable worlds, the fraction that develop life, illuminated where knowledge ends and imagination begins. The Loeb scale works the same way, a mirror held up to our uncertainty. In the quiet of a planetarium or under an open field, the idea feels almost poetic. Picture a future where each new interstellar visitor earns a number broadcast alongside its name, Atlas 5.4, a future 1, maybe 2.3. The scores would drift across news tickers like whispers of probability, guiding the global conversation between wonder and restraint. Telescopes from Chile to Hawaii would adjust their domes not from panic, but from measured curiosity. Behind this framework lies a deeper call that science, at its best, is a collective act. Loeb urges cooperation across borders because the sky belongs to no nation. A comet crossing from the northern hemisphere to the southern does not change its chemistry at customs. If we ever face evidence of another intelligence, it will not recognize our divisions. A shared scale could therefore foster shared vigilance, an international watchfulness that honors both skepticism and imagination. Of course, scales cannot capture everything. They cannot weigh the human pulse of excitement when data defy expectation. They cannot measure the trembling of a graduate student seeing a spectral line that should not exist. They cannot express the mix of awe and fear in realizing that something once thought impossible might be true. Those feelings remain beyond number, and perhaps that's as it should be. Quantifying wonder is not about replacing emotion, but protecting it, from dismissal on one side and hysteria on the other. In a way, the Loeb scale is an ethical gesture. It asks us to treat each mystery fairly, to give it space to prove itself, to hold judgment until the evidence matures. It embodies the same patience that astronomers use when stacking hundreds of faint images into one clear picture. Each exposure alone means little, but together they reveal the hidden light. So too with anomalies. Each may seem trivial until layered with others. A scale ensures that none are lost to noise. As Atlas drifts closer to the Sun, its number may rise or fall. New data could show it is simply a carbon-rich comet, dropping its score towards certainty. Or perhaps the next observation will uncover another improbability, nudging it upward. Either way, the number changes nothing about its beauty. The glow remains, the orbit remains, the invitation to look remains. The scale merely helps us keep our footing while gazing upward. And somewhere beyond calculation lies what no measurement can confine, the sense that we are living through a chapter of cosmic autobiography, the universe writing itself into our awareness one visitor at a time. Numbers may frame the story, but wonder still fills the page. There is a quiet kind of bravery in asking questions that might never find answers. Science, though dressed in the language of precision, is built on that courage, the willingness to look foolish for the sake of clarity. Avi Loeb's persistence springs from that soil. To him, doubt is not a flaw in the scientific process, it is its pulse. When he asks whether Atlas could be more than a comet, he is not claiming certainty, but defending the right to wonder aloud. The courage to question begins with humility. The night sky humbles by design. Every star we see has already lived and changed by the time its light reaches us. The photons entering our eyes tonight left their sources before human history began. To study such ancient messengers is to accept our smallness within time. Against that backdrop, Loeb's questions about interstellar visitors feel less like provocation and more like reverence. He looks up and admits, we do not yet know enough. In astronomy, progress often hides inside discomfort. When Copernicus placed the sun at the centre, he disturbed centuries of belief. When Hubble measured galaxies retreating from one another, he shattered the notion of a static universe. Each leap forward began with an inconvenient question, one that made the world momentarily uneasy. Loeb's hypothesis about technological objects, though controversial, follows that lineage. It doesn't demand belief, it invites scrutiny. Skepticism itself is a form of faith in reason, in data, in the slow honesty of measurement. But skepticism can harden into fear, the fear of being wrong, of ridicule, of stepping beyond what colleagues will tolerate. The boundary between caution and paralysis is thin. That is why questioning matters. It keeps science alive, supple, able to stretch toward new possibilities without snapping. Consider the process of discovery at its most fragile. A graduate student in a dark observatory, watching a faint signal appear on a monitor. The data are messy, uncertain. Noise could mimic a pattern. But the impulse to investigate is irresistible. That impulse is the same one that guides every great advance, from the first detection of pulsars, once called little green men because the signal was too regular, to the realization that gamma-ray bursts were cosmic, not human in origin. Each mystery began as an absurdity before it became textbook fact. To question is not to reject consensus, but to keep it honest. Theories, like stars, cool over time. They crystallize into structure and begin to resist change. But the cosmos does not pause for our comfort. It throws new anomalies into our path as if to test our flexibility. Atlas, with its improbable orbit and curious chemistry, is one such test. It asks whether we can look again with beginner's eyes. There is also an emotional dimension to scientific courage that rarely makes it into journals. Behind every hypothesis lies a person confronting solitude. The universe answers no one directly. Its responses come in photons, neutrinos, gravitational waves, forms of silence translated into numbers. To persist in that quiet, to interpret meaning from it, is an act of endurance. Loeb's defiance of easy conclusions is part of that endurance. He is willing to stand at the edge of knowledge, where evidence thins and imagination begins to shimmer. Throughout history, those edges have been fertile ground. When Newton wondered why the moon did not fall, gravity was born. When Vera Rubin noticed galaxies spinning too fast, dark matter entered our lexicon. Each revelation began as discomfort, a mismatch between expectation and observation. Atlas offers another mismatch. Its brightness, alignment, and mass all whisper of something unusual. Perhaps nature alone can explain it, perhaps not. Either way, refusing to look would be the greater failure. The culture of science often hides its emotional heartbeat beneath layers of caution. Papers are written in passive voice, conclusions softened by error bars. Yet beneath that restraint beats a shared wonder. Astronomers are dreamers disciplined by math. They feel awe the way sailors feel the pull of tides, quietly, persistently, with respect. Questioning within that tradition is not rebellion but gratitude. It is a way of saying thank you to the universe for being stranger than expected. At the same time, courage in science must pair with humility. Every answer opens 10 more questions. To stand before that endless recursion without despair requires grace. The cosmos has no obligation to make sense in human time. It unfolds across billions of years, its logic vast and impersonal. We catch fragments, spectra, pulses, gravitational ripples, and build meaning from them like children arranging seashells into constellations. To question within that scale is to practice cosmic patience. Loeb's insistence that we remain open to possibility does not reject skepticism, it complements it. True skepticism is not dismissal. It is curiosity armed with discipline. It asks for evidence but never shuts the door before the knock. When Atlas defies expectations, a good skeptic leans closer, not away. That lean, that willingness to examine instead of deny, is the quiet heroism of science. For those who look up at night through a telescope's eyepiece, questioning becomes almost meditative. You focus, breathe, adjust, and let the light settle. Each observation is an act of trust. Trust that the photons arriving have something to teach. trust that your patience will extract meaning. The courage to question is not loud or combative. It is gentle, sustained attention. It's staying awake a little longer, even when fatigue tempts you to close the dome and go home. If Atlas turns out to be an ordinary comet, then courage will have lost nothing. The act of inquiry will remain beautiful in itself. We will have added one more data point to the great experiment of curiosity, and if, by some sliver of chance, it proves extraordinary, then our questions will have paved the way to understanding rather than disbelief. Either outcome honours the same principle, that to wonder sincerely is to live awake beneath the stars. In the end, the courage to question is the same force that fuels the expansion of the universe. Both arise from energy that refuses to settle, that stretches boundaries outward. In galaxies, that energy becomes motion. In minds, it becomes curiosity. The cosmos grows by expansion. Knowledge grows by asking. And so, like the universe itself, we keep reaching, slowly, patiently, infinitely. Criticism is as essential to science as curiosity. Without it, knowledge hardens into myth. As Avi Loeb continued to voice his hypotheses about Atlas and other interstellar objects, the chorus of skeptics grew louder. Some accused him of chasing spectacle, of mistaking anomalies for evidence. Others argued that every puzzle he presented could be solved with simpler physics, no aliens required. The debate unfolded not just in journals but in headlines, a rare moment when public fascination met professional caution. At the heart of the disagreement lies a philosophical divide. One camp holds that extraordinary claims demand extraordinary evidence, until an anomaly violates natural law beyond reasonable doubt, invoking technology or intent risks undermining the credibility of science. The other camp believes that the refusal to even entertain such possibilities narrows the imagination that makes science thrive. Loeb stands at that boundary, insisting that open-mindedness is not the same as gullibility. To his critics, he answers gently but firmly, the danger of ridicule should never outweigh the danger of complacency. History supports his point. In the early 20th century, meteorites were dismissed as superstition. Rocks could not fall from the sky. Later, when radio astronomers detected a regular cosmic signal, the first label they gave it, half-jokingly, was LGM for little green men. The pulsar's discovery became one of the astrophysics' greatest triumphs, and a reminder that skepticism should test, not smother, curiosity. Yet the critics are not villains. Their caution comes from love of truth. Every scientist knows how easy it is to be deceived by data, to see patterns that dissolve under better instruments. Bias can masquerade as insight. Noise can mimic signals. Healthy doubt keeps the field honest. In that sense, both sides of the debate serve the same master, evidence. They simply disagree on how wide the door should open while evidence gathers. Behind the arguments lies a more human tension, reputation. Academia rewards certainty, not speculation. To question too boldly is to risk credibility. To stay silent is to risk stagnation. Navigating that space requires balance, the same balance that comets maintain as they swing between light and dark. Loeb, for all his defiance, often describes his work in the language of humility. He knows that probability still leans toward natural explanations. But he also knows that science without risk becomes bookkeeping. Public fascination complicates everything. Once a question enters headlines, it mutates. A nuanced statement like, Atlas might merit investigation for non-natural origin, becomes, scientist says comet is alien ship. The simplification distorts intent, yet the attention brings resources, time on telescopes, funding for analysis. The media cycle, though noisy, becomes another kind of gravity, pulling awareness toward the mystery. Loeb walks that line carefully, reminding audiences that wonder and evidence are partners, not rivals. He often quotes Galileo's quiet defiance, "Eppur si muove," and yet it moves. The phrase captures a scientist's duty to observation over authority. Galileo's telescopes revealed moons around Jupiter, proof that not everything orbited Earth. He was ridiculed, censured, yet time vindicated him. Loeb sees in that story not justification for being right, but courage to remain curious when consensus hardens too quickly. The goal is not rebellion, but persistence. Still, the criticisms have merit. Improbability alone does not prove intent. Comets are complex. Their brightness depends on rotation, composition, dust grain size, and viewing angle. A single misunderstanding of those variables can inflate odds from routine to miraculous. Science advances not by ignoring these details, but by measuring them until the miracle dissolves into math. Loeb accepts that, even welcomes it, because each test strengthens the integrity of the search. He often reminds students that skepticism and imagination are not opposite poles, but complementary forces. One stretches thought outward, the other keeps it tethered to truth. Together they form the double helix of discovery. When either strand dominates, science falters, becoming either dogma or fantasy. The healthiest state is tension, alive and unresolved. From the outside, this tension can look like conflict, but to those who live within it, it feels more like breathing. Inhale curiosity, exhale doubt, repeat. Every observation cycle works the same way. A hypothesis expands possibility. Data contracts it. The rhythm continues until only what survives both scrutiny and wonder remains. That residue becomes knowledge. The conversation around Atlas follows that rhythm. The critics calculate, model, and simulate, each test sharpening the picture. The advocates refine their hypotheses, adjusting to each new constraint. Together they build a mosaic of understanding far richer than either camp could alone. Even if the outcome proves Atlas purely natural, the method, the shared process of curiosity filtered through criticism, will have justified itself. There's a serenity in recognizing that both skepticism and faith in possibility arise from the same human longing to understand where we are in the story of creation. The skeptic looks for the familiar, the dreamer for the unprecedented. But both, when honest, gaze through the same telescope and whisper the same word beneath their breath. Maybe. In the long view, controversy is temporary, curiosity endures. Once the data settle, once Atlas moves beyond the sun and the calculations harden into history, the arguments will fade into footnotes. What will remain is the shared memory of looking up together, wondering whether we just witnessed something natural or something else. That shared wondering, half skepticism, half faith, is the pulse of science itself. And when future generations read these papers or replay the recordings of that debate, they will not remember who won the argument. They will remember that in a century obsessed with certainty, a handful of voices dared to leave room for awe. Between the critics and the dreamers, the truth will continue to glide, silent as a comet, beyond the reach of either extreme. By late October, the moment everyone had been waiting for arrived. Atlas drifted into conjunction, disappearing behind the sun's overwhelming brilliance. For weeks, Earth's orbit would hide it completely. No telescope could follow, no radar could track. The data streams that had pulsed nightly across observatories fell silent one by one, replaced by patient waiting. The world of astronomy entered its quietest kind of suspense. During those invisible days, Atlas reached perihelion, the closest point to our star. There, sunlight bathed its surface with more energy than it had felt in millions of years. Every grain of dust, every molecule of gas trembled under the heat. From that furnace distance, roughly 1 astronomical unit the same as Earth's, its temperature would have risen high enough to melt most metals, had it not been moving so swiftly that exposure came in seconds. To imagine it is to picture a dark ember racing past the sun's edge, momentarily incandescent, then vanishing into radiance. On Earth, The only record of that instant lies in equations. Orbital models predict where it should have been, how fast, how close. But reality has a way of mocking prediction. A minute perturbation, 1 kilometer's deviation in a trajectory of billions, could mean the difference between escape and capture. Astronomers checked and rechecked the math, aware that while they could not see, the cosmos was deciding the outcome. Somewhere inside that blaze perhaps the object slowed. Theoretically, a comet with perfect timing could lose just enough velocity to shift from a hyperbolic path to an elliptical one, trading interstellar exile for residency. Even without engines, solar drag and sublimation can act as tiny brakes, though usually not strong enough, but usually is not certainty. And so the question remained, would Atlas stay? For those who watch the sky for a living, this waiting carried an almost spiritual stillness. The sun, so familiar in daylight, became an obstacle, a wall of fire between us and knowledge. Yet that barrier was also beautiful. The same light that blinded our instruments sustained our patience. Astronomers joked about holding vigil, comparing notes on weather, telescope maintenance, and half-formed hopes. In that shared suspension, science began to feel like prayer. Even space observatories, orbiting far beyond Earth's atmosphere, struggled to help. The Solar and Heliospheric Observatory, SOHO, and NASA's Stereo spacecraft sometimes capture comets diving into the sun, their images streaking across coronagraphs like sparks. For Atlas, expectations were uncertain. Some hoped to see a brief glint in SOHO's sensors, others feared it would pass too far behind the solar disk to register. Each morning, analysts scanned the data for anomalies, tiny, transient flickers that might be the traveller's signature, but the images revealed only the familiar turbulence of the solar wind. During those days, Loeb's team kept quiet. Speculation would have meant nothing without observation. Instead, they refined models, calculating scenarios of capture and escape. If Atlas were truly massive, as earlier estimates suggested, its inertia might keep it steady through the solar encounter, resisting the forces that usually tear smaller comets apart. If lighter, it might fragment, leaving multiple nuclei in scattered orbits. Either outcome would tell a story. Time in astronomy stretches differently. Days feel like centuries when the sky offers no feedback. Yet patience is the discipline's defining virtue. Every great discovery, from the slow confirmation of exoplanets to the detection of gravitational waves, was once a long silence punctuated by a single miraculous signal. The researchers waited for that signal now, not in noise but in the absence of it, trusting that the sun would soon roll past its position and the darkness behind would clear. To pass those waiting weeks, some turned philosophical. A comet disappearing behind the sun feels like a metaphor for all human seeking. We chase meaning until light blinds us, then must wait for the world to turn. The orbit itself becomes meditation, approach, vanish, return. We are reminded that knowledge, like daylight, comes in phases. At last, early November arrived. Observatories in the southern hemisphere pointed their instruments toward the predicted re-emergence point, a slender region of twilight sky near dawn. The data came in cautiously, first as noise, then as pattern. There it was, a faint object, slightly dimmer than before but still intact, moving along a curve that was, miraculously, less steep than expected. The numbers hinted that Atlas had slowed, just enough to graze the edge of a bound orbit. It might remain in the solar system for decades, perhaps centuries, before drifting outward again. Confirmation would require months of tracking, but the possibility alone sent a ripple through the community. The visitor had not left. Whether by coincidence or cosmic choreography, Atlas had chosen to stay. In that moment, speculation gave way to awe. No one needed grand claims, the fact itself was wonder enough. A fragment of another star's nursery had joined ours, bound now by sunlight and gravity to the same rhythm as Earth. It would share our seasons, appear in our skies again someday, a reminder that not all wanderers depart. As data refined the orbit, astronomers allowed themselves quiet celebration. The silence behind the sun had ended. The equations were right enough, the patience justified. What had been invisible was visible again, carrying scars of its close encounter but unbroken. In a universe where most visitors pass without pause, one had chosen, by physics or fate, to linger. That night, across observatories and home telescopes alike, a new stillness settled. For once, the mystery did not demand explanation. The numbers would come, but for now it was enough to know that the story continued. Somewhere near dawn, a faint smudge of green light returned to the sky. Humble yet monumental, a comet, a question, a companion. Whatever the equations finally decide, whether Atlas will linger for centuries or drift outward again, the story has already changed us. The question of its nature, its improbable alignments, its green chemistry, and its silent passage behind the sun has become part of humanity's quiet astronomy. Even if the comet turns out to be nothing more than a carbon-rich wanderer, it has forced us to look harder, to refine our patience, to remember how fragile and extraordinary observation itself can be. In the nights following its reappearance, telescopes across both hemispheres resumed their vigil. The coma, once bright green, dimmed slowly to white, as though exhaustion had set in after the near-solar ordeal. The tails spread thin, shimmering like smoke. Instruments measured the new orbit. Plotting each position against the predictions made months before, each data point arrived like a heartbeat, confirming the simple miracle of persistence. Atlas was still there. The sun had not destroyed it. Gravity had not let it go. Instead, the comet drifted into a wider, slower path, neither visitor nor native, but something in between. It joined the long company of captured bodies, asteroids trapped by Jupiter's pull, icy fragments looping from the Oort cloud, relics that come and stay. In that modest transformation lay something profound. For the first time, an object from another star had, by all appearances, accepted membership in our celestial family. Avi Loeb called it a cosmic crossing. Not proof of intent, not evidence of technology, but a quiet symbolic act of gravity, a gesture from the universe itself. A body born elsewhere now moves to our rhythms, circling the same sun that nourishes us. That image carries both science and poetry. It tells us that the solar system is not a sealed world but an open harbour, that the borders between stars are porous, that exchange is the universe's oldest language. Perhaps Atlas was always meant to stay. Its alignments, improbable though they seemed, now appear as stepping stones leading to this final curve. Each encounter, Mars, Venus, Jupiter, may have slowed it fractionally, each coincidence a subtle transfer of motion until capture became inevitable. What looked like design might simply be the mathematics of patience, the long arithmetic of celestial mechanics where every encounter leaves a trace, nature's handwriting, elegant as any engineer's plan. As the weeks passed, astronomers continued to trace its spectrum, the ratios of carbon to water, the balance of dust to ice, the faint polarization of reflected sunlight, all were logged and compared. The data told a consistent story. This was an object unlike any from our own solar nursery, yet wholly obedient to its new gravitational master. It behaved as if it belonged here, and that belonging in itself felt like revelation. Beyond the numbers, a sense of quiet pride spread through the community. The watchers had done their work faithfully, observing, doubting, persisting. They had resisted the urge to sensationalize, but they had also refused to dismiss. When the comet emerged intact, every camp found a measure of truth. The skeptics were right that physics explains more than wonder ever could. The dreamers were right that wonder drives physics to look closer. Between them, science moved forward. For those who study the sky, the return of a light after conjunction always feels like morning after a long night. Observations resume, but so does reflection. The months of uncertainty become a kind of meditation on time. The heavens teach that no revelation arrives without waiting. The orbit of Atlas is now part of that lesson, an elongated ellipse of patience drawn across the ecliptic, a story that will unfold over decades. In 1,000 years, perhaps another civilization will look up and see the same object gliding faintly between stars, its name lost but its path enduring. Maybe they will call it something else, a starseed, a relic, a promise. Maybe they will send a craft to meet it, to read in its ices the chemistry of two suns mingled. Even then, its essence will remain what it is tonight, a traveller turned resident, a reminder that the boundaries between out there and home are temporary illusions. For now, we simply watch. Through the hum of distant instruments and the hush of twilight, Atlas recedes from the sun, carrying both mystery and familiarity. Each night it grows fainter, fading toward the outer dark. Its silence feels deliberate, but perhaps it is only physics doing what physics does, transforming energy into motion, motion into memory. We translate that motion into meaning because that is what humans do. We weave stories from gravity. When Loeb speaks of Atlas now, his tone is softer. He no longer argues whether it is natural or not. He speaks instead of curiosity as a shared inheritance, something older than any single discovery. The universe, he says, is not waiting for belief. It is waiting for observation. We are its instruments, each heartbeat another data point, each question another orbit around understanding. And so, in the months after its capture, the night sky feels subtly altered. The constellations are the same, but among them drifts a new body whose light carries the memory of another sun. It circles ours now, invisible to most eyes but known to those who listened. It is the proof of connection, the whisper that not all who wander are gone forever. Atlas may fade completely in time, its tail dispersed into interplanetary dust, its nucleus darkened to invisibility. Yet its story will remain, a thread of cosmic narrative woven into human thought. Long after its orbit is forgotten, the questions it raised will continue to glow, about coincidence, about curiosity, about how far we might see if we dare not to look away. In that sense, Atlas has already fulfilled its mission. It taught us to watch again with reverence, to treat improbability not as threat, but invitation. It reminded us that the night sky is not a static dome but a living ocean, and that sometimes, from beyond its horizon, a stranger arrives, not to answer, but to ask alongside us. And now, as the story closes, we drift once more beneath the velvet sky. The tale of Atlas settles like dust along the mind, luminous yet gentle. Somewhere above, it still circles the sun, a faint ember gliding through silence, carrying the chemistry of two stars in one long curve. The telescopes have gone still for the night. The observers have packed their notebooks and dimmed their screens. Only the soft hum of the universe remains, eternal and unhurried. Take a breath. Let the idea of that traveller linger behind your eyelids, the slow orbit, the faint green shimmer, the way sunlight bends around it like memory. Think of how gravity holds everything together, stars, comets, atoms, even thoughts. The same pull that guides Atlas around the sun guides you gently through sleep, through time, through everything that drifts and returns. Perhaps tomorrow there will be new discoveries, new visitors, new equations to balance the unknown. But tonight there is only stillness, the quiet between stars, the peace that follows long curiosity. Let it soothe the mind that has spent the day asking questions. Let it remind you that answers can wait. The cosmos moves on its own schedule, and you, for this small moment, move with it. Somewhere, ancient light still travels toward us from galaxies unborn when Atlas began its journey. It will reach us long after we're gone, and others will look up and wonder. That continuity is comfort. We are part of the same observation, the same slow gaze across eternity. So rest now beneath your own sky. The questions can sleep too. The universe is still awake, keeping watch.